Well, we're going to talk about some of the off-grid solar considerations for appliances such as chest freezers, refrigerators, and microwaves. And before we actually explore the subject, got a little panel of experts here. They're going to chime in on their thoughts of the chest freezers and microwaves. And one of our experts here, and this is expert, and what did you have to say about the chest freezers, expert?
Well, chest freezers really consume a lot of power. Yeah, they consume a lot of power. They're rated 500 watts, you know.
Okay, so chest freezers consume 500 watts.
Oh yeah, and they got a big surge too.
And they have a surge.
Oh, and they're inductive.
What does inductive mean?
Inductive means that they're not resistive.
And that means what?
I'm not really too sure, but it usually takes more power if you're inductive.
Okay. And we have another expert here who's going to talk about, he had something to say about microwave ovens.
Yeah, microwave ovens are inductive too.
Okay. Microwaves are inductive. Okay, these are some of the issues that we're going to explore to get to the bottom of just exactly how much and what kind of power do these systems consume. And of course, you know, we'll see if the panel of experts here is on the mark in terms of the actual considerations that we need to think about. So to actually explore that, let's go look at the setup of a couple of real world work. And we can see right here that the power consumption for this freezer is rated at 1.35 amps. And hopefully you can see it, because from where I'm at, I can't see it. In this power rating, don't know if you can see it or not, but this one is rated at, let me see, I think it's 500 watts. Oh, amps 5, yeah. Shows a little amps 5 there, which would be around 500 watts. So, what we want to do is get to the bottom of what these things actually consume. And what you're seeing here is a little data acquisition system. It's got a little current clamp on it. A little board that you can hook to the AC line to monitor the voltage. Provides 2 channels of signals that go into this little data acquisition system. And we hooked these up and ran them on these freezers for a certain amount of time. And that's what we're going to explore. And we're also going to explore the exact nature of the power consumption of a microwave. So looking at that outdoor freezer on its coolest day to figure out what the real power consumption of it is, you'll note on the graph, first of all, that when the compressor's on, it draws right about 1 amp, which is right about 100 watts. And you can see how the compressor cycles. This is on the coolest day that I recorded it. It was a 95-degree day. The duty cycle appeared to be about 57%, so a little bit more than half the time it was on, which would have been the equivalent to, for instance, a light bulb that used 57 watts being turned on continuously. And another way of expressing the amount of power is that it was 1368 watt hours per day. Note the freezer draws 1 amp when it's running, and the data plate did say 1.35 amps, but there's always a little bit of give and take in the specifications that people put on their equipment. And this was done, samples were taken every 5 minutes. You can see it took about 1,400 samples through the whole day, and you can see the current in amps. This is typical of what the graphs are going to look like going forward. Again, on the coolest day, the performance from the data plate. There's a data plate on the back of that freezer. And this is what the manufacturer claims it will behave like at 90 degrees Fahrenheit and with a control at mid setting. And they say that the percent of running time, this is the bigger one of the two, will be somewhere between 35 to 55%. So we're on the upper end of that, but that's more or less in line with what that data plate indicates should be expected. Now, on the hottest day, which was a 109-degree day, we were up to 81% running, which is equivalent to about 81 watts or 1944 watt hours per day. You'll see there was a long stretch where it didn't even cycle. The compressor was on for however long that is. I'd have to calculate it out, but looks like a significant part of the whole day. Now, we also looked at an indoor freezer, which is a bigger freezer, 20 cubic foot indoor freezer. And that freezer, for one day, the equivalent duty cycle was 63%. It was equivalent to consuming about 68 watts if it ran continuously, which is 1632 watt hours per day. So again, it's like a 68 or 70 watt light bulb, running all day long. You can see that the cycling was pretty nominal, right around 63%. No big surprises there, but neither of these machines are anywhere near this 500 watt. And by the way, this particular freezer is the one that had the 5 amp rating on the sticker. Never seen it happen, never. Of course, turn-on surges are a different matter. So back to why are they rated at 500 watts, or why are some of them rated that way? They'll never draw it. There's a couple of reasons why manufacturers want to put 500 watts on there. One of which is the obvious freezer turn-on surges, which we'll look at in more detail shortly here. They also want to be sure that the customer connects it to a circuit, an adequate house circuit. Minimum circuits are generally about 15 amps anyway, but they're kind of like telling you don't connect it through a tiny little cheap extension cord. There are self-defrosting freezers that the defroster can consume 500 watts during defrosting, which is a very infrequent cycle, generally not more than once every 12 hours, generally sometimes less than that, and it's usually only about an hour or two long. I don't have personal experience with the self-defrosting freezers, but putting 500 watts on the side may be a tactic to allow them to rationalize to a single nameplate for a group of models. Here's the notorious freezer refrigerator turn-on surge. It goes up to a peak of like 17.6 amps peak. It lasts for about a half of a second. So it's really there. You just have to be sure that your inverter or whatever you're plugged into can support that surge. Our freezer's inductive. Well, here what we do is we plot the voltage and the current, and we can see that the current is only about 6 degrees lagging from the voltage. To be purely inductive, you have to lag about 90 degrees. The peak of the current would be at the zero crossing of the voltage. But in reality, we're only very slightly inductive. Refrigerator freezers, even during the turn-on spike, they're still not really heavily inductive. So they're inductive, not enough to spend not enough to lay awake nights over. Freezer conclusions: they don't consume 500 watts. Maybe a defrosting one might periodically, but they only consume power when the compressor runs, and they have big turn-on surges. But they're a lot more friendly to solar, off-grid solar, than people often think at first glance, because there's been a lot of technical misinformation circulated about what they do and don't do, with very few people actually measuring them with oscilloscope level um, examinations.
So that brings us to the conclusion of the first part of this. I'm going to move on to microwaves or something next, I think. So what did you guys think of that? Well, I thought that was really very informative, and I learned quite a bit from it, and I appreciate it. Well, what's your name anyway? Oh, you can call me the Shunt Czar. The Czar of Shunt Current Sensing. CZAR. Can you remember that? Yes, sir, Mr. Czar. I think this guy's a bozo. You know, I can't possibly be wrong about the chest freezer's inductive, and boy, wait till you see the inductance in the microwave, you bozo. Well, I appreciate the comments and the feedback from you guys. You seem like a very divided audience here, but that's always good. We need people to question our own ideas here. So I appreciate it nonetheless, and we'll move on to microwaves. Are microwaves inductive? Well, let me turn a few screws on the back and move a little closer to trying to find out. Well, my highly technical associate is here to help me understand why the microwave oven's inductive. Well, there's a big transformer here. There's a lot of inductance in there, buddy. Yep, a lot of inductance before the electricity gets in and does anything. It's got this big inductive thing there. Oh, okay. Well, you know, you're giving me a real education here. What's this big thing here? That's a thing. It makes the microwave. You mean it's a magnetron? Oh, yeah, something like that. Okay, and what other stuff do we have here? Oh, I don't know. I'll tell you, transformers, a lot of inductance there, you know, so beware when you're using microwave ovens. Okay, well, I think some objective testing is called for. So what we're going to do is we're going to do some objective testing. I won't take the time to film it using my Tektronix scope like I did on the other equipment, and the little monitoring circuit that I have. Actually, I used a different current sensor for this because I needed a fast one, just in case. But we'll look at some waveforms coming out of this and see if we're inductive or not. I had to get rid of that other guy to kind of intelligently point out some of the stuff that we're looking at. And what you see down in this corner is a rectifier and a filter capacitor that comes directly off the transformer and feeds directly into the magnetron. What that circuit does is rectifies the AC to create, I don't know, a few thousand volts or something to be put into the magnetron. There's its pretty cooling fins are over there, a temperature sensor on it. This is for conditioning the AC input line and probably to keep a little bit of EMI coming back out. And this is all the brain stuff. This is where the geeky guys work, but this is where the real men work. Anyway, that's the guts of it. We'll talk about that in more technical detail as we move on.
Now to the microwave. Microwave inductive. Well, here we show the turn-on surge of the microwave, which is not a surge at all. Starts out low and goes high. So there's no surge there. The input current starts out low. Now, as far as the running current, the current, which is the blue line in the microwave, is actually ahead of the voltage, which is the opposite of inductance. It's capacitive. Now, this engineer here knows why, because it's a capacitive input rectifier, which is immediately a large capacitance driving its essentially resistive magnetron load. So the microwave is not inductive. In fact, the microwave's actually a pretty friendly load aside from the fact that it consumes an enormous 1500 watts, but they're friendly watts.
So what are our conclusions after all of this? That I'm making the point that mainstream freezers are perfectly viable in off-grid solar setups. They generally consume about 100 watts, regardless of what they say on their nameplate. And that's only when the compressor runs, which means that the actual average power consumption of that device is something less than 100 watts. It's more equivalent to maybe a 60 or 80 watt device if it were running 24/7. But thanks to compressor cycling and the fact that these things draw about an amp, almost regardless of, we looked at two size freezers today. They're both about an amp. They definitely have a big surge. What that means is you want to make sure that your inverter or whatever your source of AC is can support that big surge. I'm running 2.8 kilowatt inverter on my lines that feed my refrigerators and freezers, which is a single inverter for that circuit only, because I have redundancy. If that circuit drops out, it'll switch over to my main 4 kilowatt inverter. But I'm using a 2.8 kilowatt inverter, has no problem with the surge. It's a quality inverter though. It's not made on the other side of the planet like so much of the stuff is. There's not much inductance in the load that a freezer presents to the power line. Very little. Not enough to even think about. And on the microwave, not only is the microwave not inductive, it's slightly capacitive and has very little surge. Other than the fact that microwaves just simply do consume a lot of power, like about 1500 watts, they're pretty friendly loads aside from that. Don't see a big problem there. And something to think about on the phase angle of these things, again, that I pointed out earlier, the phase angle's low. They're not inductive because the motors in them are properly loaded. Induction motors properly loaded, like on my swamp cooler that I got up and adjusted the pulley on, properly adjusted inductive motors have very little phase shift. They are not inductive. At startup they may be. They draw a lot of current at startup, but once they're up and running, they have minimal inductance. At any rate, that's the summary of everything, and there'll be one little thing we'll talk about before we totally go away. So one last little thing to show you, and this, what I'm about to describe, applies maybe even more to on-grid solar than it does to off-grid solar, but both can find this very beneficial. Personally, I consider it a necessity. Let's say for a moment that you've got your freezer full of food, nicely frozen, and you're going to go on a vacation for a while. And let's say that while you're gone, there's a power failure. And it fails long enough that everything in your freezer thaws out. It gets worse because you're gone long enough that the power eventually does come back on. And after that, everything in the freezer refreezes again. And next thing you know, you come home and you open the lid of the freezer and you pull out what you thought was frozen food, and the rest isn't real pretty. Now, in my freezer, I have a way of knowing if I've got a problem, and that method is this little cup right here. And you see the little nut on top of that cup? Let's take that nut off, and let's take the cup out. See what we've done? We've taken a cup, we poured water in it. We put it into the freezer till the water froze up. And then we put the nut on top. And the moral of this story is, if you come home and the nut is in the water or in the ice, don't eat the food. I've done a gag article on this little technological development, and I'll leave a link in the description for the video.